Hi, everybody. So let's use Sylow's theorem to try to figure out whether there can be any simple groups of small order that are non-abelian. So remember, a simple group is a group which has no proper normal subgroups. And the smallest one we know of is the group A5, which has 60 elements, plus all the abelian ones, which are the cyclic groups with p elements where p is a prime. So are there any others with order less than 60? So we're going to use Sylow's theorem to answer this question, but we're going to, let me get a few tools together so that we can get through all of the possibilities. So the first result we're going to use is that if G is a finite group whose order is a product of two primes, then it's not a simple group. Even more, if the big prime Q is not congruent to 1 mod the small prime P, then G is actually abelian, it's cyclic. And the proof of this is an application of Sylow's theorem. So first of all, we know that, first of all, if there's only one Sylow P subgroup for some prime P, then it's normal. Because all of the Sylow P subgroups are conjugate. And if you had one of them and you took its conjugate and you got another one, then the group wouldn't be normal. But if no matter how you conjugate it, you always get the same one back, then it's normal. So if there's only one Sylow subgroup for a particular prime, then that gives us a normal subgroup. So let's let n sub q be the number of Sylow q subgroups in G, which has pq elements. So what are the possibilities for nq? Well, by Sylow's theorems, we know that nq is a divisor of pq and it's congruent to 1 mod q. But the divisors of pq are 1, p, q, and pq. And q is not congruent to 1 mod q, and pq is not congruent to 1 mod q. So, and p is less than q and bigger than or equal to 2, so p is not congruent to 1 mod q. So the only possible number which is left, which is a divisor of pq and is congruent to 1 mod q, is 1. So nq has to equal 1. For the second part, suppose that q is not congruent to 1 mod p. Well, we do the same argument, but for np. And the possible values for np are 1, p, q, and pq. pq is not congruent to 1 mod p. Sorry, p is not congruent to 1 mod p. pq is not congruent to 1 mod p. So the only possibilities are 1 and q. Earlier, we were able to rule out p because it was too small. Here we don't have that, so we have to have the actual hypothesis. We're told q is not congruent to 1 mod p, and that forces np to equal 1. So in this particular case, where the order of G is pq, q is bigger than p and q is not congruent to 1 mod p, we have two normal subgroups. We have h of order p and k of order q, both normal. And in that situation, we know that their intersection has to just be the identity, because if you're in a group of order p and a group of order q for different primes, the intersection would be a subgroup whose order divides both p and q and therefore is 1. But also we can show that these groups commute, because let's look at h, k, h inverse, k inverse, where h is in h and k is in k. So on the one hand, we know that k, h inverse, k inverse is in h, because when you conjugate H, you get H back because it's normal. So this is in H times H, which is H. But on the other hand, we can group things this way. And then it's in HK H inverse times an element of K. And of course, this is K again. So HK H inverse K inverse is in H intersect K and therefore must be the identity. So that means HK H inverse K inverse equals E, or HK equals KH. So the groups H and K commute with one another and their intersection is the identity. If you take their product, HK, that's going to be isomorphic to H cross K by the results on internal direct products. And since this has PQ elements, it must be isomorphic to G. So G is actually isomorphic to the product of ZP cross ZQ. And by our work on abelian groups, that tells us that G is cyclic of order PQ. If it happens, by the way, that you don't have this hypothesis, if Q is congruent to 1 mod P, then the group could be non-abelian. And of course, we know a very simple example of that. S3, it has order 2 times 3, and 3, which is the Q, is congruent to 1 mod 2, which is P, and S3 is not cyclic, it's non-abelian. So that condition is necessary if you want to conclude that the group is abelian. Okay, so that's one classification result that we have from Sylow's theorems. The second one requires us to think a little bit about what it means to have a group action. So remember that a group action is a set X together with a map that takes an element of G and an element of X and produces a new element of X. One way to think about that is that an action is equivalent to giving a homomorphism, phi, from G into the set of permutations of X. Remember, the permutations of X are the set of bijective maps, F from X to X, with group operation composition. And the map is phi of G is supposed to be a map. And what is the map? It's the one which you get by applying X, by applying G. And if you compute phi of G1, G2, well, on the one hand, that's FG1, G2, which is the function which takes FG1, G2 and applied to X gives you G1, G2X. But by the properties of a group action, that's G1 of G2X, which is G1 of FG2 of X, which is FG1 of FG2 of X, which is FG1 composed with FG2. So maybe a better way to put it then is that phi of G1, G2 is FG1 composed with FG2, which is the same as phi of G1, phi of G2, since the multiplication in the permutation group is just composition of functions. So you can think of a group action as a homomorphism from the group into a permutation group. And from that, you get a nice little corollary, which says, suppose that NP is the number of Sylow P subgroups in G, then if the order of G does not divide NP factorial, G is not a simple group. And the proof is the following. You let G acts on the N sub P Sylow P subgroups. And by the previous little lemma, this means we have a homomorphism phi from G into SNP. And of course, this is a group which has NP factorial elements. Now, there are a few possibilities here. Could this map be injective? Well, if the order of G does not divide NP factorial, then that means that this can't be injective, because if it were injective, then the image the image would be a subgroup that's isomorphic to G, but you can't have, but the order of G, but that would contradict Lagrange's theorem, because the order of G is not a divisor of NP factorial. The other possibility is that this map could be the trivial map. Could it be the case that phi of G equals the identity for all G? Well, that can't happen either, because we know that G permutes all NP of the Sylow P subgroups. So this would mean that G fixes the Sylow P subgroups. And that would, there's various ways of thinking about that. It either means there's only one Sylow P subgroup. It would mean that NP is equal to 1. And if that was the case, then if the order of G does not divide 1 factorial, that's going to always be true, but it's then going to be the case that G is not simple because NP is going to be 1, and that means there's going to be a unique Sylow P subgroup. And in the middle case, where it's not injective and it's not trivial, then we know that its kernel is a proper normal subgroup. So this gives us a way to tell, because the kernel of a homomorphism is always a normal subgroup. So if the map isn't injective, then the kernel is not the trivial group, and therefore we found a normal subgroup in G, and it's not injective. It's not simple. Okay, so let's think about what we know now when we look at groups of order less than 60. Well, if the group is of prime power order, then it's either ZP, in which case it's simple and abelian, or it's of order a power of P, and that's not simple because we know that such P groups have non-trivial center. And the center of a group is always a normal subgroup. So if we look at all the numbers up to 60, the primes give us simple but abelian groups, and the prime powers give us groups which are not simple. We've already shown just up above that groups of order PQ are not simple. That's this earlier result that we proved. If you take the largest prime divisor of n, where n is the order of the group, and n has no divisors that are congruent to 1 mod p other than 1, then n sub p has to be 1, and G has a normal subgroup. So this is another criterion which follows from Sylow's theorem. And if you go through, and I'll spare you this, if you go through all the numbers up to 60, stopping at 59, and you apply these 3 tests, you can rule out possible orders for simple groups for all the numbers except 12, 24, 30, 36, 48, and 56. So now let's rule out those. Let's do 12, 24, and 48 first. The argument is the same in each case, so let's do 12. We're going to look at the number of 2 Sylow subgroups. N2 has to be odd, and it has to divide 12. But if you look at the divisors of 12, the only odd ones are 1 and 3. If N2 is 1, then G is not simple because it has a normal subgroup, a normal 2 Sylow subgroup of order 4. G is not. If N2 is 3, well, then we're in the situation we use the fact that 12 does not divide 3 factorial, which is 6. And again, we get that G is not simple. So we're forced to have N2 equals 1. The same thing works for 24. The divisors of 24 are 1, 2, 3, 4, 6, 8, 12, and 24. 1, 2, 3, 4, 5, 6, 7, 8. The only odd ones are 3 and 1. If n2 is equal to 1, not simple. And similarly, 24 does not divide 3 factorial. So n2 equals 3, not simple. And 48, the divisors are 1, 2, 3, 4, 6, 8, 12, 16, 24, and 48. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is that right? This is 2 to the 4th times 3. Yeah, so it has 10 divisors. The only odd ones are 1 and 3. And the same two cases that give you n2 is equal to 1, not simple. And n2 is equal to 3. 48 does not divide 3 factorial, so it's not simple. Okay, what about 56? I'm going to come back to 30. That's the hardest one. So 56, there's a proof in the text, and it goes like this. Let's look at n7. So the divisors of 56 are 1, 2, 4, 7, 14, 8, 14, and that's 1, 2, 3, 4, 5, 6. This is 8 times 7, so it should have 8 divisors. 14, 28, and 56. So N7 has to be congruent to 1 mod 7. And there's two possibilities. It's either 1 or 8. Those are the only divisors of 56, which are congruent to 1 mod 7. If N7 is 1, then G is not simple, because it has a unique Sylow subgroup with 7 elements. Otherwise, if N7 is 8, then each Sylow subgroup are isomorphic to Z7. And no two of them, if the intersection of any two of them has to be the identity, because two copies of Z7 would intersect in a subgroup of Z7, but the only subgroups of Z7 are the trivial group and the whole group, and if they're different, it has to be the trivial group. So let's count up elements of order 7. So the elements of order 7, there are 6 in each copy of Z7, 8 copies of Z7, total of 48 elements of order 7. And in addition, there's the identity element, one element of order 1. So what's left? We've accounted for 49 elements. 56 minus 49 is 7. We know that there must be a Sylow 2 subgroup with 8 elements. And there's only room for 1, because there's only 7 elements that don't have order either 1 or 7. They must all have order dividing 8. And so there's room for 1 Sylow 2 subgroup, which therefore implies that it is normal. So in this case, what happens is either there's a normal Sylow 7 subgroup or there's a normal Sylow 2 subgroup. There's no room for anything else. What about 36? Well, 36, we can go back to our n factorial trick, but using 4 instead of 3. The point being that we look at n sub 3. The divisors of 36 are 1, 2, 3, 4, 6, 9, 12, 18, and 36, I believe. 1, 2, 3, 4, 5, 6, 7, 8, 9. So N3 has to be a divisor of this, and it has to be congruent to 1 mod 3. So 1 is congruent to 1 mod 3 and 4 is congruent to 1 mod 3, but nothing else here. These are all divisible by 3, so they're not congruent to 1 mod 3, and 2 is not congruent to 1 mod 3. So N3 is either 1, which implies that G is not simple because it has a unique Sylow subgroup of order 3, or N3 is 4. But in that case, we would have to have 36. 36 does not divide 4 factorial. 36 does not divide 24. And therefore, by our result on n factorial, this implies that G is not simple. And all of this leaves us finally with the case of 30. And 30 is different from these other numbers because it's a product of 3 primes. And so we need a little bit of a trick to do 30. So let's look at the number of 3 Sylow subgroups. So the divisors of 30, just to get this on the record, is 1, 2, 3, 5, 6, 10, 15, and 30, I believe. So 1, 2, 3, 4, 5, 6, 7, 8. Yes, those are all of the divisors of 30. So N3 has to be a divisor of one of these numbers, and it has to be congruent to 1 mod 3. So the only possibilities are 1, or the only other divisor of it, which is congruent to 1 mod 3, is 10. And let's take a look at N5 while we're at it. N5 has to be 1 mod 5. So N5 would have to be 6 or 1. Those are the only possibilities. And then if you wanted to look at N2, N2 would have to be 1 or 3 or 15 or 5 or 15 because it has to be odd. So there's a lot of possibilities for N2. Let's take the case of N5, and let's suppose that N5 is equal to 6. So that means that there's a Sylow subgroup, let's call it K, with 5 elements, and the normalizer of K must be equal to K, because the index of the normalizer, which would be G n of K, is the size of the orbit, which is 6. And so since K has order 5 and the index is 6, these are the only possibilities. Great. So now let's take an element of order 2 in G. So let's suppose sigma is in G of order 2. And we can think of sigma as giving a permutation of these 6 Sylow 5 subgroups. And because, and we know that it can't fix any of these subgroups, because if it fixed one of them, it would have to belong to the normalizer, which is the stabilizer under conjugation. But the stabilizers only have order 5. They can't contain an element of order 2. So sigma has to take these 6 elements, and it has to do a permutation of them of order 2 with no fixed points. And the only way it can do that is if sigma acts like 3 transpositions. So it permutes the Sylow 5 subgroups in pairs. 3 pairs get interchanged. In other words, and that therefore inside this copy of S6, sigma is an odd permutation. So now let's consider, as we said before, we have a homomorphism phi from G to S6 coming from the permutation action on the 6, 5 Sylow subgroups. And then we have the sign permutation, which takes a sign character, which takes us to Z mod 2. And because sigma acts like 3 transpositions and is odd, this map here is onto. And because it's onto, its kernel has to have 15 elements. Its kernel can't be trivial, and its kernel can't be the whole group, So its kernel has to be a proper normal subgroup. So the even permutations in G are a proper normal subgroup. And so by all of this, we have ruled out the existence of a normal subgroup of any order up to 59. And when you get to 60, you reach the alternating group on 5 elements, and that does turn out to be a simple group.